One sec, there we go. Okay, welcome, and let's get started. Natasha is going to talk about linear transformations of vertex operators of Hall-Littlewood polynomials. Feel free to start whenever you're ready.
Okay, so I would like to thank again for the invitation to speak at this very inspiring seminar. I was very excited to find out about its existence. So thank you very much. It's a great honor for me. And before I go into details, technical details, I would like to give some outline of the story, just to give some impression of what is the main idea. And here is the plot of the story. So there are many, there are symmetric functions, like, for example, Schur functions. This is our role model, which play important role in many parts of mathematics. Like, for example, they are characters of GLN. They play a role in Schubert calculus calculations. They are solutions of KP hierarchy. So they have many interesting combinatorial properties, and they are quite important. And they have a lot of different relatives. For example, their close relative is Schur Q functions. If these are like determinants, these are more like Pfaffians. And there are also many different variations where you change something in the definition and you get something else. They appear in different applications, in different things where you need combinatorics. So Schur functions and Schur Q functions, they are specializations of a bigger family, which is called Hall-Littlewood polynomials, which are symmetric functions with the parameter t. So if you put t equals 0, you get Schur functions. T equals -1, you get Schur Q functions. And the story which I would like to tell today is based on the fact that these symmetric functions, they can be realized using vertex operators, applying quantum fields to a vacuum vector. And this is a very useful tool, and it allows to prove different properties of these symmetric functions. So my talk today is about application of vertex operators to properties of symmetric functions, to combinatorics. And here is what we are going to do. So we will take vertex operators that realize Hall-Littlewood polynomials, and we will slightly modify them in a very simple way, using a matrix with complex coefficients. So it will be infinite matrix. We will apply some linear transformation, and we will get a new family of symmetric functions. And since this transformation is very simple operation, the properties of these functions are going to be very easy to prove because all hard work is done here. And then we could think, okay, so since it is a simple transformation, there is no use in that. However, this is not the case, because it turns out that after we prove general stuff about these linearly transformed Hall-Littlewood polynomials, we can take different examples of matrices, insert into this construction, and then just for free get different examples and their properties. And these examples we can find in the literature in various areas of mathematics. So I will name some examples without going into details, where symmetric functions of this kind, they are part of this construction. So I try to advertise here a tool where the work is very easy to do. So why do I have these people on the bikes here? So here you have just to go a little bit uphill to do a little bit of work. And then it's very beneficial because then you just go down the hill and everything just goes on itself. So you get the properties for free, you just enjoy it. And my favorite part of this story is that these guys, Schur functions, they are solutions of KP hierarchy. They are related to soliton theory. And using our methods here, we can prove that these examples which appear in these constructions, they are also solutions of KP hierarchy, and moreover, any solution of KP hierarchy is going to be part of this story. So that's like the best, maybe was the motivation for me to do this project. So this is just in few words what is this story about, and now there will be all details, notations, and all the things. So since Okay, so since we are going to talk about symmetric functions, all notations are going to be here today in the language of symmetric functions. So lambda is going to be the ring of symmetric functions. So these are polynomial kind of functions. We can think about them as polynomials, which do not change if we permute the variables. And sure symmetric functions is the famous example, very important, which comes from representation theory. This is combinatorial definition. They have different applications, and in particular, they form a linear basis of this ring. Also, we will need three families of symmetric functions which create lambda as a polynomial ring. The first ones are power sums, and I ask you to remember this notation. So these are symmetric functions of this kind. So any symmetric function is a polynomial in power sums. That's an easy theorem. And we will need complete symmetric functions, which are given by this formula, elementary symmetric functions, which can also be considered as generators of ring of symmetric functions as a polynomial ring. And here we will do everything in terms of generating functions or quantum fields. So for each symmetric function, we can associate operator of multiplication by this function, and this we will do for h's and e's. And this will be quantum fields that will appear in many definitions. So I ask you also to pay attention to these ones. And also we can consider adjoint operators. There is a bilinear form, so we can look at adjoint operators. So this will be our notation for the quantum fields of adjoint operators. And here is how it's sometimes written in the literature in terms of power sums. So it can be familiar if you have seen vertex operators in this form. And it is not difficult to prove commutation relations between these quantum fields. They are of this kind. So it's just some computation in algebra. Okay, so now a lot of algebraic structures interesting algebraic structures act on the ring of symmetric functions because this is a polynomial ring. So we can think about this as part of boson-Fock space. So we take countably many copies of this ring and create a bigger space. And then we can introduce different things which act here. And again, I'm just going to write down how we can write down them in terms of those quantum fields that we already introduced. So Heisenberg algebra is of course acting here. This is an algebra, Lie algebra, which has these kind of generators and these kind of relations. If we combine them in formal distributions, we can write down these generators through formal delta function. And the standard way how to make Heisenberg algebra to act on a polynomial ring is by multiplication and differentiation. And for us, the meaning of these P's is going to be exactly power sums, those symmetric functions. Charged free fermions is a Lie superalgebra with two types of generators, which create and annihilate stuff. So these are relations, or equivalently in terms of formal distributions. Again, this here is the formal delta function. And we can also define the action of charged free fermions on the space that consists of symmetric functions using those multiplications by complete symmetric functions by h's, adjoint for e's, and the other way. And it is an exercise that follows from those commutation relations that here we will get indeed relations of charged free fermions. Or sometimes we are interested in neutral fermions, which have just one generating series. This is the relation. And this is a relation in terms of distributions. And this one also can be written in terms of e's and h's. So how we do this? So we take fermions here and we multiply by one more copy by e's. So you see that this is almost the same. But we also restrict on the subspace of lambda, which is generated by odd power sums. So this is the boson space for neutral fermions. So it's smaller than this boson space. Okay, and there is also gel infinity, but we don't need it. Okay, and now I'm going to introduce Hall-Littlewood polynomials, and I'm going to introduce them not by the combinatorial formula, which will appear later, but also as a result of action of quantum fields. So let us take the ones which were charged free fermions, this H and E, and also multiply by one more series with parameter T inside. And let's do a similar thing for the other one. So let's consider these two quantum fields of operators acting on symmetric functions, but now we look at power sums in some variable T. And one can prove relations, commutation relations between these quantum fields. Now they are not that nice, but still quite manageable. And let us take a collection of these quantum fields with different variables and apply them to vacuum vector. We will get the formal distribution. And let's expand this formal distribution in monomials. So what we will get? We will get some elements in lambda. Yes, it's going to be polynomials. Yes, it's going to be polynomials. So we're going to get some elements in the vector space. And of course, each of them is going to be just the result of several applications of these coefficients to this one. And what we are going to get here, we're going to call Hall-Littlewood polynomials. Because when lambda is a partition, these are exactly Hall-Littlewood polynomials, which we know from McDonald book and from some other places. And vertex operator presentation, which we use here as a definition, is due to Naihuan Jing from 1991. So this is what we have here. And this is the definition which we usually see, the combinatorial definition of Hall-Littlewood polynomials. So the statement is that if we compute the result of application of these operators when lambda is a partition, then we can compute it as a symmetric polynomial given by this formula. So when lambda is not a partition, but some integer vector, you see here we have some integer vectors, it's going to be something else. So this formula works only for, let's say, partitions. And what I would like to pay attention here, this formula, is this monomial, because we're going to change it. Okay, so this is the place where we're going to make changes. So this, in our construction, we'll have a change here. So please pay attention to it. And just a remark that if we insert in this formula t equals 0, then we will get the ratio of determinants, and this will be exactly sure functions as lambda. And these gammas, which we used here, these ones, where are they? These ones. So they will become fermions, charged free fermions. And if we insert t equal -1 in this formula, so we will get a formula which is definition of sure Q functions. So Pfaffian kind of symmetric functions. And the corresponding vertex operators will become neutral fermions. So these two stories about charged free fermions and neutral fermions, they combine together if we introduce parameter T. And that's convenient because then we can study Hall-Littlewood polynomials and just do one computation and then restrict it to t equals 0, t equal -1. So you don't have to do the same thing more than once. Okay. And one of the important properties of Hall-Littlewood polynomials and its specialization is the stability property. So what does it mean? That means that if instead of last variable we insert 0, that's the same as to take instead of n+1 variables, n variables. So for example, if we take example of a stability, or more simple, like where we can see it. So let us take power sum, the first power sum, just the sum of variables. So if we take n of them and make the last one 0, it's the same as to take n-1 of them. So here is an example of stability. And it is possible that we don't have a stability. for some symmetric polynomials. And here is example. So if I put here xn equals 0, I will not get the same result as if I use this formula with n minus 1, because n will stay here, not n minus 1. So this is not a stable symmetric polynomial. So it is symmetric in n variables, but we cannot extend it into symmetric function in infinitely many variables in consistent way. And in our part of interest, it's a big deal because we want to have an action of infinite dimensional algebras, and therefore we need infinite dimensional spaces. And therefore lambda n, the symmetric polynomials of n variables, is not enough for us, it's too small. And therefore the stability, I will just stress, oh, this is stable or this is not stable, and some examples which will appear later in this talk. So, and the Hall-Littlewood polynomials are stable, which is very good for us. These are good guys for our story. And now we're going to do some changes and to get something slightly new from our Hall-Littlewood polynomials. And actually, we can do this not only for Hall-Littlewood vertex operators of Hall-Littlewood polynomials, but for any kind of like quantum fields. And this is what we are going to do here. So for a moment, let us forget about the Hall-Littlewood polynomials. Let us take any quantum field acting on some space W. And we will keep in mind that for our applications, we will take an element in our vector space W and apply these quantum fields to get some formal distributions. And we will be interested in coefficients of this formal distribution. So this is usually what will be of interest for us in these quantum fields. And coefficients will be, of course, given by this formula. Now let us take an infinite complex valued matrix. And let us take these coefficients of this quantum field and just modify them, multiplied by this matrix. As a result, we get something. And a priori, this something is not a well-defined object because this is an infinite sum. And if we want some algebraic structure for our quantum fields, we will very quickly run into question whether we can multiply these operators. For example, here we multiply them, whether we can multiply them, because this is something infinite. And therefore, very often, we may want to have some restrictions on how this matrix look like if we want to have some reasonable properties of our new object. And in particular, so here, this is infinite matrix, it goes in all four directions, and assume that it has all zeros on the left, starting up to some point. So this part is all zeros everywhere. If we have this property for this matrix, then it guarantees us that the things that we defined are well-defined linear operators on the space W. So we can apply them to the vectors of W. It's going to be fine. Moreover, so let us look at this boundary between zeros and non-zero part. And let's assume that it is an increasing function when I goes to infinity. So that it goes in steps increasing. If we have this situation, then actually when we combine these new operators in a formal distribution, it's going to be even a quantum field. So it will be nice. So we can even work with this as a quantum field. And we started with the quantum field, which we applied to a vector, and we've got some formal distribution. And what we may want to do, so of course we get some new elements f tilde lambda with our new operators applied to vector f. And actually we don't need a new generating function for them. We can take exactly the same formal distribution f of u and re-expand it instead of monomials here, take some formal distributions which are related to matrix A with the coefficients. So we need this matrix to be invertible to have this definition work here. So we can just take exactly the same formal distribution, but re-expanded in new kind of basis. And then the coefficients will be these new linearly transformed vectors. Okay, so that's also a good thing for us. And sometimes, for example, we want to keep commutation relations of our quantum fields. And here are examples how you can preserve commutation relations for the algebraic structures which are very popular in applications. For example, you started with quantum fields which realized the charged 3 fermions. So this was the relation. And you applied to each of these to psi pluses and psi minuses, you applied linear transformation, you multiplied by matrices. Then the new operators will satisfy relations of charged 3 fermions if and only if matrices A and B that you used here will be inverses of each other, but you also need to make a slight shift here because of 1/2. So this is how you can guarantee that your new operators will be again charged 3 fermions. Or if you have neutral fermions, this kind of relation, and you decided to make this simple linear transformation, then if you want to keep the relation, then you have to have your matrix with this kind of inverse, so that it has a symmetry with its inverse, this kind of like, yeah. For Heisenberg algebra, so where you have generators which satisfy this relation, if you transform it, then your matrix A must satisfy this kind of equation where matrix P has some numbers, integer numbers on the second diagonal, and A is, so here is honest transpose, so some kind of equation here. Okay. So this was just, until now we did it for any quantum field and maybe to quantum fields which realize our favorite algebraic structures. Now let us apply this to Hall-Littlewood polynomials vertex operator presentation. So I remind you that we have a quantum field of this kind. These are multiplication by complete symmetric functions, elementary symmetric functions, and these are adjoint operators for elementary symmetric functions. So some operators acting on this space, combining quantum fields. And if we apply these coefficients to 1, we get Hall-Littlewood polynomial. So we agreed that we are going to call this Hall-Littlewood polynomial. And we do this operation which we just introduced. We take these coefficients of gamma plus of u and multiply them by, transform by matrix A. And as a result, by the general procedure, we get here some new symmetric polynomials, which will also depend on parameter t. And then, so you can see that I have my bike going down here. It's very easy, because just it's a linear algebra thing, to prove different things, because we already know them for Hall-Littlewood polynomials. So first of all, the stability property of our new polynomials comes just out of I mean, you just do it and that's it. So that means that we can consider them as infinite symmetric functions. So we can continue to work with infinite dimensional algebraic structures here. Also, we talked about re-expansion. Our new polynomials will come out of generating function for Hall-Littlewood polynomials, which is well known. But we just have to take a new basis for this formal distribution. So we have to do something like this. Moreover, suppose that in addition to those properties which we already asked from our matrix A, so that our situation would be nice, it has a block structure. So we divide it into 4 parts. Here we have only one on the 0 rows and columns. So here we have something, here we have something, here we have only zeros, and here we also have something. So if we have this situation that, so especially important that we have 0 here and here, then we can use almost the same combinatorial formula, at least for some of these coefficients. Namely, when lambda is a partition, we can write down that our coefficient is going to have almost the same kind of formula, but here in blue, the only thing that is changed. So in Hall-Littlewood polynomials, here we had x1 to the power lambda 1, xn to the power lambda n. And now in our linearly transformed Hall-Littlewood polynomials, there will be polynomials. Those coefficients are related to the coefficients of this matrix which we used here. So they just come from here. And one important detail which is cannot be avoided here is that we start here with the first power of x. So the constant coefficient will be always 0 here. So if I take this formula and I allow it to have zero here, like a non-zero constant coefficient, this formula in some cases will not be a stable polynomial. So it cannot appear in our construction canonically. So maybe you can do something with that, but it's not just going, I mean, you have to do something extra to understand what's going on here. So nevertheless, so our linear transformed Hall-Littlewood polynomials are different from Hall-Littlewood polynomials by this part. And if you look around, you could see that this kind of modification of Hall-Littlewood polynomials appears very often in different parts of mathematics. So it's quite common that people have to change this part because they count something. So it's a very common situation, either for Hall-Littlewood polynomials or for specializations. And I would like to just name some of the examples without explaining in details what are they, because probably it would be just like it would need more notations, and those who work with them, they could do a better job in explaining. So what happens here? So suppose that we put t equals 0 in the formula on the previous page. Then we would get a determinant of this kind, which is different from Schur functions, classical Schur functions, that instead of x to the power k, we put here some polynomial. Okay. And for example, we can, instead of x to the power k, put a geometric series here up to x to the power k. So we have to start with x because we don't want constant coefficient to be anything but 0. So then there are some dual basis, which is always important. It is rational functions here. And this is the resulting Schur symmetric function, linearly transformed Schur symmetric function. And it has properties which we listed before, and also there will be one more which I will stress later in the end of these examples. So another typical situation where instead of power of x, we look at shifted by sequence power of x. So we take a sequence of numbers, a1, a2, and so on. And instead of x to the power n, we write down this polynomial where each time we shift by an element of a second. So it's called multi-parameter of x, power of x. And here we choose a basis. Again, some technical details we have to put started with x. Some dual one, and we will get linearly transformed Hall-Littlewood polynomials. So they also appear in the literature, in the works of our colleagues. For example, these two Japanese mathematicians, they have these Hall-Littlewood polynomials for general T related to these ones. In their computations for complex cobordism theory. So there is, I just want to say that they appear in some papers which are not absolutely, like, completely different kind of story. And if we take specialization t equals 0, we will get some kind of multi-parameter analog of Schur symmetric function. And the situation here is that there are many different multi-parameter analogs of Schur symmetric function, where instead of x to the power k, you look at this kind of parameter, and they have different properties. So some of them are called double Schubert polynomials, factorial Schur functions, Frobenius Schur functions. And here I would have to state that the resulting linearly transformed symmetric polynomial Schur functions that we got here, they did not match any examples that I saw in the literature, that I know from the literature. So this is what we get in our construction, which we discussed today. And I would like to compare it with the two most close examples. So this is the classical one, the classical definition of Schur symmetric functions. So the ones which we use in representation theory of GLM. So it has X, and here we have lambda, and then in the power. And in our linearly transformed case, we have to break it into two parts. One stays the same as before, it's just a monomial. The other one is multi-parameter case. It just comes from the fact because we used Hall-Littlewood polynomials as our construction. And we can see that this is intermediate case from a thing which combinatorially was defined that are called sometimes factorial Schur functions, if these are particular values of parameters, where we substitute all of this with the multi-parameter power. And the fact here is that the classical ones, of course, are stable ones. These are Schur functions, not only polynomials, are Schur functions. Our ones are also stable because that follows from our definition. But for these ones, it is well known that they are not stable, and therefore they are not very convenient for applications in representation theory related, for example, to boson-fermion correspondence or vertex operators. So they're not quite, sometimes they're not quite convenient. Okay. So this is how this one is related to these two examples. So that's what I wanted to say about T=0 case. And surprisingly, if we look at specialization T=-1, which corresponds to Schur-Q functions, the linearly transformed Schur-Q functions coincide exactly with the multi-parameter analogs, which were already defined earlier in some settings. So combinatorially, they were defined by Vladimir Ivanov in 2005, but they appeared earlier in works of Maxim Nazarov, and also later they were not like a couple of years ago. They also were studied by Sahi, Salmosyan, and Selganova. So what are these? So there are central elements of universal enveloping algebras which are related to Capelli identities. And there was a beautiful question how to compute eigenvalues of the central elements on irreducible representations. And in the case of Lie superalgebras of type Qn, the eigenvalues are given exactly by polynomials which appear here also. So in this case, when T=-1, we have our Schur-Q polynomial, linearly transformed polynomials. They are exactly the things which were considered by other people. So that's really fortunate and good luck for us. Now, if we go a little bit down and we consider the sequence where all a's are the same, it is just going to be shifted power of x-1 to the power k-1. And for general T, these kind of polynomials that we got, they also already have we could see, can find them in the literature. For example, there is an important paper by Alexei Borodin on symmetric rational functions. And later there is a big, there are many papers which relate these symmetric rational functions with 6 vertex and 5 vertex models with R matrices and all that stuff. And the particular case of symmetric rational functions, so when instead of functions, rational functions, you get polynomials, so degeneration is going to be exactly the case that we get here from our situation. And of course, in particular, specialization T=0 is going to be a particular case of that. But moreover, if we change variables in specialization T=0, we can get up to some renormalization Grothendieck polynomials, which also there is a, I mean, it's a very lively part of combinatorics today. So it's like many people study them right now. So they also so one can find these polynomials as well. So in the papers of many people, it's just like a lot of literature on that. Okay, so by this list, without explaining what are these symmetric polynomials, I just tried to convince you that our construction that we discussed today, it appears quite often in different areas of mathematics, in algebraic geometry, in algebra, in representation theory. So it's not just, so it's quite natural. And
I have a question, Natasha.
Yeah.
So when you were giving this specializations, the t equals 0, t equals -1, you didn't give us A, right? Is it hard to describe what A is in that case? Is it a very special matrix that you're grabbing, or is it very natural?
So they are basically coefficients of these polynomials. So it's not difficult, but it would be just, so here, these would be elementary symmetric functions of these A. So it's, so F, this F, it contains an F minus K. The coefficients of these polynomials are exactly coefficients of this matrix A.
Great, thank you.
So yeah, so no, it's not difficult. No, it's just extra space on the slide. That's the only reason. Okay, so I want to continue to collect benefits from our approach. So we have these many different examples of symmetric functions which appear here and there and everywhere. And we can say for all of them at once using our construction that they satisfy different, like the same kind of property. We just substitute a different matrix A in each particular case. For example, it's very easy to describe a Jacobi-Trudy formula in this case, which expresses sure symmetric function through complete symmetric functions. So here you just multiply this by these coefficients. Okay, so stability property, again, I say that it's immediately, so usually it is technical exercise to show that your definition gives a stability property, but once you know that this is part of this construction, it's just like follows immediately. Again, generating function. So for sure symmetric functions, the generating function has a very nice form. So this is the generating function for sure symmetric functions. So how does it look like? We take complete symmetric functions. We make this kind of determinant. So we take L of this series and then expand in powers of U. And when alpha is a partition, this is going to be exactly sure symmetric function. So that's why I call this series, generating series for sure symmetric functions. Now, as we mentioned before, we can take exactly the same series, but just re-expand it in new basis. And we will get those examples depending on what kind of basis we are going to take here. And this part, which I'm going to explain right now, is probably my favorite part, because this was like the reason why I actually got interested in this construction, in making this construction. Namely, the description of polynomial tau functions of K-peak hierarchy. So first I will make a statement and then I will go in details. So this construction allows to prove easily that all these examples that we got, they are solutions of bilinear identity, which corresponds to cadence of Petriashvili hierarchy. And moreover, any polynomial tau function can be expressed as linear transformation of sure symmetric function with appropriate choice of metric. So it is part of this construction with particular, with the appropriate choice of matrix A. So let me just tell a little bit more what is K-peak hierarchy and what is K-P solutions. So there is an equation, which is a partial differential equation on a function u in 3 variables, x, t, and y, which is called cadence of Petriashvili equation. And it is a very famous equation because it is a soliton type equation. So it has soliton solutions. So what means soliton solution? It is a solution that looks like a wave. It propagates like a wave with the time t. And it has a remarkable property that it does not change its shape, whatever it means, as long as it moves like in some direction. So this is usually called soliton. And moreover, soliton type solutions, they behave in a very unusual way when they meet each other. Because when they meet each other, they don't destroy each other, but they exchange impulse or energy, and they just continue to travel as they did before without breaking each other. So this is very unusual, and especially because this is a nonlinear partial differential equation. And also it is unusual that solutions of this equation can be found explicitly, not just approximately some numerical data, but real formulas with exponents and yes, so you can express them through exponents. And KP equation, so that's why these equations were of great interest for mathematicians. And it turns out that KP equation is not just an equation on its own, but it is part of a long list, countable list of equations which are compatible, and they create KP hierarchy. And on the next slide, I'm going to show very quickly the transitions, how one can approach to one of the approaches how to study KP equations, KP hierarchy. It's only one direction, so there is no the direction which goes to Lax equations, for example. So this is the path which leads to representation theory. So KP hierarchy is studied by people from different areas of mathematics, by representation theory specialists, mathematical physics, numerical, by numerical methods, algebraic geometry, partial differential equations. So many different people study it in different ways, and it's just really an object on the crossroad of many areas of mathematics, and it's really amazing. So KP hierarchy is a collection of equations, of partial differential equations on some function u. And it turns out that they can be written in terms of so-called Hirota derivatives, so that they become a collection of algebraic equations on a function tau. And all these countably many equations, they can be actually considered or interpreted as coefficients of Taylor decomposition of just one identity. So if you write down Taylor coefficients here, each of them, so you will get many equations. And then this one, it has many different interpretations in representation theory. For example, it can be considered as a condition that you have an element in the orbit of the vacuum vector under the action of the group gel infinity, or some other things. And for us, for our story, when we talk about symmetric functions, we can think about this as this kind of bilinear identity. So I'm going to go to this green island, and I'm going to just do a little bit more explanation of what is going here. So from KP hierarchy, we go somewhere here. And now I'm going to discuss here. So we're again back in the boson-Fock space, which is a ring of symmetric functions generated by power sums. We have charged 3 fermions which act here. And since they act here, we can write down this kind of operator. And we can apply this to a tensor square of some element from symmetric function, and check whether we get 0. So we can look at this kind of equation. This is called bilinear KP identity because it corresponds to KP hierarchy. If you can solve this one, you do some change of variables, you find a solution of KP hierarchy, if you're lucky that it is not zero. And solutions of this one, they're called tau functions. And polynomial tau function means that tau is an honest polynomial in powers, not a series in those, but an honest polynomial in p's. So then it's called polynomial tau function. And example of a solution is sure symmetric functions as lambdas. This is the result of Sato. So you have to express them in as a polynomial in power sums, then it's going to be a tau function. And now I'm going to tell how to describe all polynomial tau functions. So there are two ways to do this. And both are related to generating functions. So we're going to modify generating function for sure symmetric functions. So this is what we wrote down a few slides ago. So if we expand it and look at the coefficients, when lambda is a partition, this is going to be a sure symmetric function. And let us do the following modification. Let us take this SU, which encodes sure symmetric functions. Let us take a collection of complex valued Lorentz series. And okay, so here it's just, I should give some other name for this with the head, for example, or T of U. So we take this, this one and multiply by Lorentz series and re-expand. We get some new coefficients which are going to be linear combinations of these guys. So the result which we were able to obtain with Victor Katz and Johan van der Loo is that these coefficients are also going to be solutions of bilinear KP identity. They are polynomial KP tau functions. And moreover, any polynomial tau function can be written in this form. You just have to choose appropriate Lorentz series to modify this function, generating function. So this is one way. And the other way is related to what we did today. Namely, we again take the generating function for sure symmetric functions, but re-expand it in a new basis. Instead of u to the power lambda, you take here some formal distributions. You get here coefficients. Then these coefficients are going to be polynomial tau functions. And again, any polynomial tau function is going to be a part of the construction which we discussed today. It's going to be a linear transformation of sure functions for appropriate choice of matrix A. So why this is good for us? This is good for us because we have many examples coming from different papers for which we know that they are going to appear here in this kind of series. And therefore, we know right away that there are going to be examples of tau functions of KP hierarchy as soon as we express them through power sums. So this is how we can describe polynomial tau functions. Okay, so I would like to stop here. So this is the things which I wanted to tell about this construction. So thank you very much for the attention.
Thank you so much, Natasha. This is very interesting. Let me stop the recording and we'll ask